configuration. Let's get started! Electron configurations are a simple way of writing down the locations of all the electrons in an atom. As we know, the positively charged protons around the nucleus of an atom tend to attract negatively charged electrons. While these electrons all stick within the atom because of their attraction to the protons, they also mutually repel each other, causing them to spread around the nucleus in regular patterns. This results in beautiful geometric structures called orbitals that represents the distinct regions around the nucleus that each electron traces out. The energy levels or shells are essentially the same as Bohr's energy level numbers. The letter N and a whole number are used to represent the energy levels. For example, N equals 1 is used to represent the first energy level. This number describes the average distance from the nucleus. The larger the value of N, the further away it is from the nucleus, and the more energy the level contains. When N is equals to 1, it contains one subshell which is 1s. When N is equals to 2, it contains two subshells which is 2s and 2p. When N is equals to 3, it contains three subshells which is 3s, 3p, and 3d. When N is equals to 4, it contains four subshells which is 4s, 4p, 4d, and 4f. Also remember that S subshells can accommodate only 2 electrons, P subshells can only accommodate 6 electrons, D subshell can accommodate 10 electrons, and F subshells can accommodate up to 14 electrons. 3 rules are applied in deriving the electron configuration. What the Aufbau principle says is that the electrons will feel the lowest energy first before they move on with higher energy levels. So that's why hydrogen would have one electron in the lowest energy level, which is 1s, in that orbital. Now, what's the electron configuration? Well, there's slightly a different format when we know this much information about the electron configuration. We'd write it as 1s with a subscript or 1 in the power. Here's the breakdown for that one. So 1s, which is the 1s subshell, and then the baby numbers as superscripts. Those are the electrons, so 1s1 means that I have one electron in the 1s subshell. Let's move on to helium. Helium has 2 electrons, so I'm going to put in 1s just like I did for hydrogen. I have room for another in the 1s subshell, so the other electron to make helium's 2 electrons is going to be in the 1s subshell. Now, notice that the arrow is pointing down. There's a reason for that. The electron configuration would be 1s2. The reason for that arrow pointing down is the Pauli exclusions principle, and they say that the electrons in the same orbital will spin in opposite directions. Keep in mind these electrons are negatives, and negatives don't want to be near each other if they don't have to do so. Spinning in opposite directions make them a little bit more comfortable. Now let's move on to lithium. Lithium has 3 electrons in it, one in the 1s and the other in the 1s. So now that I've filled my 1s, I have to move on to the next highest energy level, which is the 2s. So my configuration becomes 1s2, 2s1. If you look at these baby numbers, here are the superscript numbers 2 and 1. That should always add up to 3. In this case, but I mean it generally, it should always add up to the number of electrons that you intend on putting in the configuration. So that's the way to kind of check it when you're done. Let's move on to beryllium. Beryllium has 4 electrons, 2 in the first shell, 2 in the second shell, and so this would just become 1s2, 2s2. Now that we're getting the hang of this, let's keep going for another couple elements. Boron has 5, so 2 in the first shell, 2 in the 2s subshell, and I'm not going to move on to 3 because the 3s subshell requires way more energy than the 2p subshell. So I'm going to start filling the 2p subshell, so this would become 1s2, 2s2, 2p1. Okay, let's move on to carbon. Carbon has 6 electrons, 2 in the first shell, 2 in the 2s subshell, and then you'd think that I just have 2 electrons here in the 2p subshell, and that's true. But the way that this is drawn out here, where both electrons are in the first orbital and the other 2 orbitals are blank, yeah, that's not gonna happen. Imagine getting on a bus, seeing that there's an open seat and there's a seat that has someone in it. you're gonna go for the open seat before you're forced to buddy up with someone in a seat that's already occupied. This is called Hund's rule. Hund's rule essentially says that the single electrons will fill each orbital in the same subshell on their own before pairing up. And so instead of having something like this, we'd have more something like that, where we'd end up with 1s2, 2s2, 2p2. But really, we have to kind of know what's going on with these electrons. Here, they're spinning in the same direction and they're not going to start to buddy up until they have to. Now we learned that we have a more specific or advanced way of saying where the electrons are. There's something that can immensely help you, and that is the periodic table. Let me just slide the helium over to the right next to hydrogen for a second. And then I want to kind of point out that there are 4 areas in the periodic table that you may not be able to unsee once you see it. Let me kind of break out the periodic table a little bit. If you notice, the first major section only has 2 per row, and that kind of mimics the fact that as subshells, we can only have up to 2 electrons. So this tall tower here on the left, we call it the S block. Then let's just read this like a book, top to bottom, left to right. If you look on the right side, we'll see that the 6 elements wide, and that resembles the 6 electrons that can fit in a p subshell. In the center, we've got 10 elements wide, and that represents the D block or the D subshell. And then of course, the bottom 2 rows, that's the F subshell. If you count up, there's up to 14 elements there. So now I'll show you all of this to tell you that you can really use the periodic table to help you figure out what the electron configuration is for any element. Let me show you a hydrogen. Hydrogen would be 1s1, heliums would be 1s2, and then I'm just gonna skip down to the next row here. Now I'm in the second shell of electrons, so lithium would have this. This is just the end of its electron configuration: 2s1, beryllium 2s2, boron 2p1, carbon 2p2, and I can keep going until p3, p4, p5, p6. Now my p subshell is filled, and what do you know? I'm also at the end of the periodic table. I now have to start over in the third row just like I would. I would move to the 3s subshell, and now there's nothing immediately next to 3s2. So I keep going over to 3p1 through 6. And then I'm gonna go in the 4s subshell, but now that that's filled, I can then go back to the 3d subshell. And that's where this 3d block comes from. It doesn't match the row number, but you know that that's what we're doing with these orbitals. And then I continue on with 4p and so on. So the point here is, the periodic table is incredibly helpful, and the more you practice these electron configurations, I think that's when you'll realize it more, that the periodic table is truly a beautiful work of art and science come together. I do want to show you some of these electron configurations can get pretty long. So let's look at magnesium's 12 electrons, meaning 2 in the first shell, 8 in the second shell. That's 2 plus 2s plus 6 plus 2p. And then 2 in the third shell. So the electron configuration is 1s2, 2s2, 2p6, 3s2. That's a lot to say and it's a lot to write. So here's a trick. I want to show you, if I just look at this piece here, which is 1s2, 2s2, 2p6, that is the electron configuration for neon. Neon, being the most recent noble gas that we would have gone through, is at the end of the periodic table all the way to the right. And think of this like I have neon, and then I just have 2 more electrons, one in the 3s and the other in the 3s. If I can think of this way, then I want to do, and I'm allowed to do this. Replace the neon configuration part of this with just neon's element symbol in a square bracket, like this. So this is a time saver. You could go to Google and search up magnesium's electron configuration, and it's going to show you this instead of the full 1s2, 2s2, 2p6, 3s2. It's just gonna show you neon 3s2. This is called the noble gas shorthand trick or noble gas configuration. I hope you guys learned a lot in this lesson. Thank you for watching.